square. I've gone back to the 2D world for a little bit. It says find the equation of the locus of points that are equidistant from 2, 3, and 5, 3. So it's pretty easy to draw a picture of this. Here's the point 2, 3. You go over 2 and up 3 and put a point there. You call that point A maybe. This is point A. This will be point B. Point B is over 5, up 3. So there you go. And I'm asking for all the points that are equidistant from A and B. So to get started, sort of the easiest point to find, it would be the midpoint. You know, if you were standing right here in such a way that you were halfway between the 2 points, you'd be equidistant from A and B. Okay. Now, we can find that if we want. The midpoint formula, or the midpoint of 2 coordinates, is always the average of the x values, average of the y values. That's sort of that's a way to find it. Average x, average y. So in our case, 2 plus 5 is 7 over 2 is 3.5. And the average of 3 and 3 is 3. So there is one point that's on the locus. Think of the locus as a set of points that satisfy the condition. Okay. Now, where else can I go? So let me ask you to consider another point for a minute. Suppose I went up exactly 1 unit from here, and I went to the point 3.5, comma 1. Not comma 1, sorry, comma 4. Okay, exactly 1 unit above that midpoint I just found. And the question I'm going to ask you is that point also equidistant from A and B? And the answer is yes. You can see that a couple of ways. We're interested in that distance versus that distance. And we're trying to ask, are those 2 red distances the same? They are, if you just imagine, we draw a right triangle here. So let's use a different color. Suppose I drew 2 right triangles. What do you notice about them? Well, their bases are the same. Their heights are the same, right? So the hypotenuses have to be the same. So this piece and this piece have to be equal in length. So this point, 3.5 comma 4, is also equidistant from A and B. Let's continue. If we were to go up again to, or down here somewhere, maybe I went to the point 3.5 comma 0, and using the same reasoning, if I drew 2 right triangles, well, there you go. You'd have 2 hypotenuses, which are also the same. Right? So what does this mean? It means that all the points along that line would be equidistant from A and B. And that equation is simply x equals 3.5. It's an easy equation to find. All right? Now, more importantly, just some language you should be aware of, this line, x equals 3.5, is the perpendicular bisector of the line segment that connects A and B. Okay, that's what it is. It's a perpendicular bisector of the line segment that contains A and B. All right, so what if I just change the question ever so slightly? So suppose we're still going to stay in this 2D world, but I wanted all the points equidistant from 2, 3 and 5, 1. So let's draw this picture and see what happens. Ready? So here we go. We draw our axes. 1, 2, 1, 2, 3. Here's the point 2, 3. 1, 2, 3, 4, 5, 1. Here's the point 5, 1. And again, we can start off right away by finding the midpoint, because we know if we went to the midpoint, we'd be equidistant from both of these given points. All right, I'm going to call this point A again and this point B again. So the midpoint, the average x value would be 3.5, because you have 2 plus 5 over 2. And then the average y value would be 3 plus 1 over 2, or 2. So there's your midpoint. 3.5 comma 2, somewhere around there. Okay, so this distance here and that distance here are the same. Now, we just showed in the previous example, what we're really interested in are all the points along this perpendicular bisector. Because any one of those points, you're going to be able to make 2 right triangles, which you know will be congruent and have the same hypotenuse, and everything will be fine. Okay, so how do we do that? Well, we need to think a little bit about things. Well, first off, we actually know the direction of this line, don't we? We know that this green line that I drew, this perpendicular bisector, is perpendicular to the line segment AB. So I'll call this line L. line L is perpendicular to line segment AB, well, that means that L, or I should say it this way, the slope of L is the negative reciprocal of the slope of AB. That's what we know. Okay? So let's do that. We can actually get the slope of AB pretty quickly. I'm going to call that M sub AB. And the slope would be 3 minus 1 over 2 minus 5. Or it would be 2 over negative 3. So the slope of line segment AB is negative 2/3. So that means, that tells us that line L, the slope of line L, would be the negative reciprocal 2/3 or positive 3/2. Okay? And actually, I'm done now. Because I know two things. Right? I know line L has slope 3/2 and passes through the point, what did we say, 3.5 comma 2. That was the midpoint. And once you have that, you can use the point slope form of a line and get your equation. So that's not bad at all, actually. The point slope form of a line looks like this. Y minus y1 equals m times x minus x1. So y minus 2 equals 3/2, x minus 3.5. So this is the equation of all, or I should say the locus of points equidistant from the points 2, 3, and 5, 1. Okay? We're going to consider a new problem. We're going to give you 2 points in the 3D world now and ask for the same question. What are the locus of points, or what's the equation of the locus of points equidistant from points A and B? And while we proceed through this, I want you to think how this is somewhat analogous to the problem we just did. Right? So there's one easy point you can get right away. You know right away that the midpoint of these 2 points, A and B, has to be on the equation of the locus. Okay? So we know that. So we can get the midpoint the same way we do in the 2D world. The midpoint would just be the average x, the average y, and then the average z. Okay? Now, it's not going to be pleasant to look at in this problem. So I'm sorry for that in advance. But let's try and write it out. So what do we have here? We're going to have the x coordinates added together and then divided by 2. So 1 plus, or I should say 1 minus really, right? 1 minus rad 2 over 5 over 2, comma. The next point is going to be 2 plus 2/5. Okay, so 6/5. Make sure everybody agrees with that. All right, and then lastly, this one, I don't know, so I'm just going to leave it. 5 minus rad 2 over 3 over 2. Now, you can convert these to decimals or find out the decimal approximations for these things, but that's the exact midpoint. That's the point that's equidistant from both points to start off with. Okay, now, take a look at this picture. And this is where you have to sort of think three-dimensionally. Okay? If I do the following, if I decide that I'm going to pick a point somewhere on this plane, now I can't really call this plane the perpendicular bisector. Perpendicular bisector usually means line, but it really is. This plane I've drawn is perpendicular to the line segment containing A and B. So that's a right angle there. Okay? And it passes through the midpoint of A and B. So what I want to convince you is that all the points in that plane are really equidistant from A and B. That's what I want to convince you of. All right, so I want you to imagine I picked some point out here, and I'll just call it P sub 0 for a minute. I drew a line segment from A to P sub 0. I'm going to draw another line segment from P sub 0 to B. And what I'm hoping is that those two line segments will have the same length. If they do, then this plane I've given you really does the job. Well, it doesn't take long to get that to work. Draw a line segment from the midpoint to here, and then have this realization. What you really have here are two right triangles again. That's a right triangle, and that's a right triangle. I know that because of how I created this plane. I said that this plane, right, is perpendicular. All the points in this plane, or all the vectors in this plane, I should say, are perpendicular to the vector that goes from B to A. Or I could think of it this way. If I drew any line segment in that plane, it would be perpendicular to this vertical line segment from A to B. So that's how you know there are right angles here. And actually, you're done. Because the two blue line segments are congruent. This is shared. So the two hypotenuses, or hypotenuse, whatever, have to be the same. Okay? So this works. We really just want the equation of that plane. But we're almost there, believe it or not. So don't be nervous. Look, equations of planes look like this. A times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. Where x0, y0, and z0 represent the coordinates of a point on the plane. Now we have that already. Here it is. Here's your x0, here's your y0, here's your z0. The midpoint has to be on this plane. A and B, A, B, and C, these guys, those are the coordinates of the normal vector to the plane. But you know the direction of the normal vector. The direction of the normal vector is the direction of the line segment from B to A. Right? So I can create that vector pretty quickly if I just subtract the points. The normal vector to this plane, right? By definition, we made the plane perpendicular to this blue line segment from A to B. So the normal vector is in the direction of that line segment, A to B, B to A. So that's it. So I can get that vector. So the normal vector is going to be the point B, a point A minus the point B, I guess. So we'll do it that way. We'd have 1 minus negative 2/5, or 1 plus, oh, not 2/5, sorry, rad 2 over 5. And then you're going to have 2 minus 2/5, or 10/5 minus 2/5, or 8/5, I think. Yep, that's good. And then you're going to have 5 minus negative rad 2 over 3, or 5 plus rad 2 over 3. Now, actually, I should be careful. This is not a coordinate. This is a vector. It's a vector because it's a set of differences between x, y's, and z's. All right, so now we're done. We have the direction. We have the point. It's almost analogous to the 2D world. In the 2D world, we did everything in rectangular equations, but we had the direction when we said we knew the slope, right? When we said, hey, we know the slope of line L is 3/2, it's sort of like giving you a direction vector, right? This is the direction vector 2, 3, actually, is what it is. Okay? And then we knew a point it went through, which is the midpoint. And that's what I'm saying here. I'm saying this is your direction. This is, well, it's not really a direction vector. It's perpendicular to the plane, right? And then we have a point it goes through. It's not a perfect analogy, but whatever. All right, so here we go. That thing times x minus this. And I don't know, why not write it this way? Because it's what it is. 8/5 y minus 6/5 plus 5 plus rad 2 over 3 times z minus 5 minus rad 2 over 3 over 2. And that has to equal 0. So there you go. This thing in red is the equation of the locus of points equidistant from the two given points in 3 space. So we're going to switch gears a little bit. We're going to go back to vector valued functions, and I want to talk about how to find the length of these things. So we'll title this arc length of space curves. Okay? All right. So sort of the famous example that we looked at. We first started looking at vector valued functions. I asked you to think about this thing. Okay, you can write that this way also. Cosine Ti plus sine Tj plus T, oops, hold on a second, T times K. All right? So we know this is the helix, and we know sort of what it looks like. Here's X, Y, and Z. It starts at the point 1, 0, 0, and then it sort of loops around and up, and it stops up here at the point 1, 0, 2 pi. Well, at least it did that for the domain we were interested in. So we did a domain from 0 to 2 pi. Okay, so that's called the helix. So when I talk about arc length, what I'm really saying is this, that if I had sort of like a flexible ruler, right, or a piece of string or something that I laid out right along this path in 3 space and then measured the length of it, that's what I'm asking you about. How long of a walk is it to walk up the helix from 1, 0, 0 to 1, 0, 2 pi? That's the question that we're trying to look at. Okay? All right. So I'm going to a little bit of background, and this is going to happen pretty quickly. So here we go. Ready? So let's just go back to the 2D world for a minute. And imagine that we're on this curve somewhere, and we're going to move a very small distance along this curve. So we're going to move from here to here. Okay? And while we're at it, let's pretend we know our position on here is given by the parametric function x of t comma y of t. Okay? That's what this thing does. All right. So if we have a nice smooth curve and we take a small enough section of it, then the secant line from the points would be very close in total length to the length of the arc. Okay? Now, for those of you who might not believe me about that story, try something like this in your calculator. Graph y equals x squared. And then clearly you see a nice U shape here and so forth. You know that there's a vertex down here at the parabola where it stops going down and starts going up. Whatever you want. Pick 2 points. Okay? And then, or pick a point and keep zooming in on it. And if you keep zooming in on it, what you're going to notice is that curve starts, this very curved parabola starts to look very straight. Okay, and parabola has that property. If you keep looking in really, really closely, smaller and smaller intervals, it starts to straighten out. Okay, it's a property of all differentiable functions. Okay, so what I'm going to say is I'm going to call the length of that blue thing L. I'm going to say that L estimates the length of the arc, the red arc that we're interested in. Usually you call arc length S. L will approximate us very, very well. We can get an approximation by that by doing the following. It's some small change in x. Here's some small change in y, and you see a little right triangle there. Right? Sort of like a little bit of a slope. We've gone over a little bit to the right and a little bit up, and we created a right triangle. We can get L. L is just the Pythagorean theorem. It's dx squared plus dy squared. Okay? Now, this is sort of limiting, no pun intended, because you're looking at a very, very small section of the curve, right? And what I'd really like to do is I'd like to do this over and over again. I'd like to pick more secant lines and add and keep doing this thing where I have these right triangles that I'm going to create. That right triangle is almost flat there. If I did this one, it would be like that. I'd like to have a bunch of these little right triangles, a bunch of these L's, and add them together. As a matter of fact, I'd like these little L's to be as narrow as possible. So if this is beginning to sound like an integral, that's because it is. Okay? So here's what we do. Now, we know we can get positions along the curve if we subbed in values of t. So I want to get t involved. So what you can do is this. We said L equals dx squared plus dy squared. I'm going to multiply that by dt on the outside, and you have to ask yourself, okay, what could I multiply by on the inside that would preserve this, that wouldn't change its value? In other words, I would multiply by 1. And the answer to that is multiply inside by 1 over dt squared. So if you look at this new expression I've just written, now let's be clear here that dt squared is under the radical. This radical comes down. This is equal to that. Right? I like this better because now it's sort of, I'm writing it as a function of t, and now I can start to add up. So here's what I really want to do. I want to add up a bunch of these. So an integral does that. So I can write an integral from t equals a to t equals b, some starting value of the parameter to some finishing value of the parameter. That makes sense because for any curve that we drew, if we drew a section of a curve, this would correspond to the point x of a comma y of a. In other words, sort of the initial point of the curve where I started paying attention to this path in 3 space. And over here, this is x of b, y of b. That's what that is. All right, so down here I have from t equals a to t equals b of this thing. I'm going to write this slightly differently. I'm going to write this dx squared over dt squared plus dy squared over dt squared dt. That definitely looks like an integral. Call this L. One more thing I'm going to do just so I can get a look at this. This is from t equals a to t equals b. And if you look carefully at it, this is really dx dt squared plus dy dt squared dt. So there you are. You have, right? You have an integral that tells you how long or how much path we've traversed along some kind of curve in the 2D world. Okay? That's all that is. So to make the jump to 3D is actually it's pretty easy. The length changes from a to b. These are values of t, by the way. The square root of dx dt squared plus dy dt squared plus dz dt squared dt. And you can draw a little picture to justify that if you have any doubts in your mind. Watch. Right? Let me show you that quickly, and then we'll finish. So suppose here you are in the x, y, z space, okay, and I have a section of a space curve here, right? Well, let's call it a section of a space curve. If it's small enough, it'll look like a straight line. So we'll just say, hey, that's L, right? Now, what do we know? We know we could make a right triangle somehow out of that, right? The only problem would be is that this lower leg here, this leg here that I'm tracing over, may not be parallel to the y-axis or to the x-axis. It might be moving some angle with respect to those. So then I could draw another right triangle parallel to the xy plane. And if you do that, you're actually done, because watch what happens. That little piece there is dy. That's a change in y. That little piece is dx. And then this little red piece is a dz. Okay? Now watch what happens. I don't know what this base is, this red base here. So that red base in there, I'm just going to call that, I won't use D. I guess I'll use M. So what do I know? I know that m squared equals dy squared plus dx squared by Pythagorean theorem. And then I also know from this triangle that L squared equals m squared plus dz squared, right? And this should remind you of the derivation of length in the 3D world. Sub this in. So you get L squared equals dy squared plus dx squared plus dz squared. You take the square root of both sides, you multiply through by dt over dt, and you'll get exactly this integral.